Okay, today we're going to look at a neat technique that we will use in our next section, but it comes in handy in lots of places. It'll come in handy on some old problems that you've already done, and it'll also come in handy down the road in further chapters. Okay, so you can kind of read through these and guess what we're going to talk about today, but let's look at an old example, okay, a limit problem. These are the first problems we looked at in the calculus class, and we started off looking at limits and saying we will plug in the input value into this function and see what comes out. If we get out a number, we're good. That's the limit. Limits can be the same as function values. That's not very exciting because it's basically a pre-cal idea that we're just going to plug in numbers into functions and see what comes out. From time to time, we had a couple of scenarios rise up that required us to do some more work. So in this case, if we substitute a 2 into x in every location we see an x, we're going to get out 0 in the numerator and 0 in the denominator. That was one of our bells and whistles problems that told us we got to do something to get the problem out of this form, and we call this indeterminate. The limit cannot be determined at this moment because 0 over 0 could end up being any number as a limit because we don't know which 0 dominates the other, etc., etc., etc. Okay, so back in the fall, that required us to factor or rationalize or expand or use some trig rules or do a bunch of other things. Today you're going to learn a really neat shortcut that's going to make most of the limit problems that we see very, very easy to do, and I think you'll be excited to do limits after today. Okay, so the rule is called L'Hopital's rule. He's French, and there's lots of spellings for his name, but I think this is the one the book uses and we'll use, I suppose. So looks like hospital, but really neat rule. It's a little bit wordy, but just work with me here because once we get through the verbiage, it's very nice. Okay, so here's what L'Hopital's rule says. It says if the limit as x approaches some number of a function over another function comes out to be 0 over 0. For example, what we just looked at here would be a situation that fits this scenario here. Okay, then the limit we're asked to do. Okay, so this limit is the same as another limit that we will be able to do in most cases very quickly here. Okay, so this limit is equal to this limit. Okay, the limit as x approaches a of f prime of x divided by g prime of x. Now, there's a couple things we should say here, and I should put in parentheses if this limit exists, this second limit, because it might not exist either. And we may need to do the rule again. So what's required here? Well, f and g both have to be differentiable to even take a derivative of f and g. So that's kind of an implied assumption here. So f and g are differentiable. But generally speaking, it's saying, hey, if you have an indeterminate limit, 0 over 0, then instead of going back to your algebra techniques that we had to do back in the fall, instead you can try this little trick here. Take the derivative of the numerator function, take the derivative of the denominator function, and then substitute in the value. If that limit comes out to be a number, that's the value of the original limit. And it seems a little bizarre. So I'm going to go ahead and just show you really quick a convincing proof, I hope a convincing proof, why it's true. Okay, so what are we starting with? We know that the limit as x approaches a of a function f is 0, and we also know that the limit as x approaches a of another function g is 0. Okay, so we're given those two ideas, and we are asked to find the limit of f over g as x approaches a. Okay, so the goal is to find this limit, if it exists. Limit as x approaches a, f of x over g of x. And at the moment, sorry, I didn't finish this thought over here, equals 0. At the moment, this limit's indeterminate, so we can't just jump to an answer here. Okay, so we've used this principle a few times, and I kind of like it. Let's replace f and g with their tangent line equations at x equals a, because when you zoom in around a, f and g, if they're differentiable, look like they're tangent lines. Okay, so what will those tangent line equations look like? We've done that many, many times. Tangent lines where? At x equals a. So f of x would be approximately the same as its tangent line at a, which is f of a plus the slope of f at a, that's f prime of a, times x minus a. Okay, that's the tangent line to f at a. That's the generic form. And then similarly, we've got g of x is approximately its tangent line. So that would be g of a plus g prime of a times x minus a. So we have two lines now that we can substitute in for f and g near, okay, near x equals a, because that's really what we're asked to do when we're finding a limit, is what does this function behave like near a, not necessarily at a. Okay, so that means that this limit here, okay, this limit that we started with, is going to be the same thing as taking the limit as x approaches a of, well, f is pretty close to its tangent line near a, so that's going to be f of a plus f prime of a times x minus a, and g of a plus g prime of a times x minus a. Okay, now what do we know about f of a and g of a? Well, these functions are differentiable, which means they're continuous, and that means that their limit at a is the same as their function value at a. So both of these functions have to be equal to 0 at a. So these two parts disappear, and as long as x is not equal to a, which it's not because we're taking a limit, these two terms cancel out as well. And look what you have, f prime of a over g prime of a. The limit is the same as this limit right here. So that's not a formal proof, but hopefully that convinces you that this will work, and we can check a couple of these the old way just to be safe. Okay, so if I'm asked to do this limit, and I want to use L'Hopital's rule, what do we do? Well, we say this is the same thing as the limit as x approaches 2 of what? The derivative of the numerator, which is 2x plus 1, over the derivative of the denominator, which is 1. Okay, so now I have a limit problem, a new one, and I'm going to substitute the 2 into the x and see if I get out a number. And in this case, we get 2 times 2 is 4 plus 1, we get 5. And since that's a finite number, that is our answer. Okay, so using L'Hopital's rule, that was kind of neat. Now, we could have done this the old way. This one's not that difficult. So let's just verify using what we would have done in August. In August, we would have factored the numerator, x plus 3 times x minus 2 over 1 times x minus 2. And we would see that these x minus 2's cancel as long as x doesn't equal 2. So around 2, this is 5. And that's what we got over here. Okay, before we go on to the next idea, I want you to go ahead, pause the video, and try 4.4, number 7. Yeah, that's 4.4. That's correct. We're jumping back a section, or a couple sections. This was actually taught early in the book, but we didn't really need this until now, so I put it off. Pause the video when you're ready to resume. Come on back. Okay, if you are ready, L'Hopital's rule also works for another indeterminate form that we've seen. So I'm going to go ahead and just stick this little arrow in here. It says if the limit as x approaches a f of x over g of x equals 0 over 0, okay, and I'm going to say or it could also be infinity over infinity, our other famous indeterminate form. So if it's this, we can also use L'Hopital's rule, and these could be negative, positive, positive, negative, 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 same idea. Both numerator and denominator are very, very large. We can still use the L'Hopital's rule technique, which is nice because now we don't have to go into force factoring, which is everybody's favorite thing in the world to do on a Saturday night. So here's an example. If we do a quick mental substitution on this, I would say, okay, the numerator is a very large positive number, infinity, and I'd say the denominator is 1 minus a very large positive number. The denominator is negative infinity. But not all infinities are created equal, so I can't just cancel these numbers out and say that the limit's negative 1. It might be negative 1, but I don't know until I do some more investigation. So because this is an indeterminate form, I'm allowed to use L'Hopital's rule, which says, okay, if I have an indeterminate limit, that is the same as taking the limit of the derivative of each part of the fraction. So the derivative of the numerator is 2x plus 1, and the derivative of the denominator is going to be negative 4x. Now, what do we have now? We still have a large positive number in the numerator, and I still have a large negative number in the denominator. So I'm no better than when I started. But this could have been an original problem, and I can use L'Hopital's rule again. So this is going to be equal to the limit as x approaches infinity of what? The derivative of the numerator, which is 2, over the derivative of the denominator, which is negative 4. And now we have a finite answer, negative 1/2. And you might recognize that's what the answer we would have gotten, because we would have force factored an x squared out of the numerator and an x squared out of the denominator. These two terms would have basically become zeros here, this one and this one, and you would have been left with a 1 in the numerator and a negative 2 in the denominator. So we can use L'Hopital's rule in this scenario as well. When you're ready, try 4.4, number 17, pause, and then come on back. Now, this is really the meat of today's lesson here, is that there are other indeterminate forms besides 0 over 0 and infinity over infinity. Those are the two most common. But these down here are also indeterminate forms. So let's talk about them real quick. Okay, we said infinities are not all created equal, so infinity minus infinity, it's attempting to just make this equal to 0, but that's not always the case. This infinity could be a lot larger than the first one. And vice versa. So this is unknown. We've got to do something about it. 0 to the 0 is indeterminate. Now, why is that? 0 to any number is 0, as long as that number is not 0. And any number to the 0 power is 1, as long as the base isn't 0. So here you have kind of a battle. How small is the base? How small is the exponent? They have a little fight. We don't know what that comes out to be. Lots of things can happen. Same thing here, 0 times infinity. This is a small number, and this is a very large number. They have a battle. We don't know who prevails, or if there's a compromise somewhere in between. Infinity to the 0. Again, a large, large base, and you have a very small exponent. You want to say it's 1? Well, some people want to say it's infinity, because this is not really 0. It's close to 0. And then 1 to the infinity is another one. You want to say, well, why isn't that 1? Well, because this is not necessarily a 1. It's something close to 1. So if it's a number less than 1 to a huge power, it would go to 0. If it's a little bit more than 1 to a huge power, it goes to infinity. Or there might be a compromise. So you must be very careful when we do our mental calculations that we're not really doing an indeterminate form and making some false assumptions. So what do you do if you run into one of these scenarios? Well, to use L'Hopital's rule, it has to become a fraction in one of these two forms. And so that's how we're going to do these, is by transforming them into an indeterminate form of either 0 over 0 or infinity over infinity. And that's what we're going to show you next, the next couple examples, is how do you go about transforming a problem that looks like one of these into something that you can use L'Hopital's rule with. Okay, so here's an example. The limit as x goes to 0 from the right, because we can't go to 0 from the left for the natural log function because there are no values on the left side of 0. But anyway, if you do a mental plug-in, this is 0 times the natural log of numbers getting close to 0 from the right. And if you think about the graph of the ln function has a vertical asymptote at 0, and the values head towards negative infinity. Okay, so 0 times negative infinity, it's tempting to write 0, but if we go back here and check, that's one of our indeterminate forms. So we have to do some more work. And the work is to put this in another form so I can use L'Hopital's rule. L'Hopital's rule says I need a fraction. So let's see if we can rewrite this as a fraction legally. So the limit as x goes to 0 from the right side, natural log of x, and let's rewrite x as a fraction. Or rewrite the whole thing as a fraction by rewriting x as something else. So let's see. The number 2 is the same as 1 divided by 1/2. Okay, convince yourself that that's correct. Now, it's not something you would do naturally to write 2 as 1 divided by 1/2, but it's legal, it's true. And so in this case, I'll write x as, I think, let's see here, x would be 1 over x. Okay, does that look correct? If you flip the guy multiply, you'll get x. So that means I can write x ln x as ln x divided by 1 over ln x over 1 over x. Okay, so if we flip the guy, multiply, or if we multiply numerator and denominator by x over x, then we'll get the original problem back. This is now a fraction. Now, is it a form that I can use L'Hopital's rule on? Let's see. The numerator is going to still be a very, very large negative number. The denominator is 1 over a small positive. So 1 over a small positive is a big positive number. So now you're in the form negative infinity over infinity, which means I'm in L'Hopital's rule scenario. I'm allowed to use it here. Okay? So I've done my job. I've transformed it into a fraction that is an indeterminate form. So let's use L'Hopital's rule, which says, let's take the limit of the derivative of the numerator, which is 1 over x, divided by the derivative of the denominator, which is negative 1 over x squared. And if we simplify this, before we try to take the limit again, we'll get something very friendly. Limit as x goes to 0 from the right of negative x over 1, which comes out to be 0. Okay, now don't just say, hey, I told you 0 times infinity is 0. That's not always the case. And we can come up with some really quick examples to disprove that if you don't believe me. Okay, pause the video and give 4.4 number 46 a try using this technique of rewriting a product as a fraction so that you can use L'Hopital's rule. Okay, this is our last example. This is one of my favorites because you've seen this before, and I've never been able to show you, I don't think, formally why it's true, why the answer is what it is, but here's our finally a chance to do that here. Okay, so what do we get when we do a substitution here? we get 1 plus 1 over infinity. Okay, now what is 1 over infinity? That is very close to 0. So you're looking at 1 plus something pretty close to 0 to a large power. Okay, so what is this? This is really 1 to the infinity. And if we go back and look at that list, 1 to the infinity is one of the indeterminate forms. So I can't call this 1. I can't call this infinity, because remember, this is a little bit more than 1. This is not quite 0. It's close. So what do? Well, I need to convert this into a form that I can use L'Hopital's rule on. Now, how do I write this as a fraction? Because the exponent is stuck here. I can create a fraction here, but then what about this x here? That's a problem. Okay, so this is kind of a neat little technique. This limit, if it exists, is equal to a number. Let's call that number k. So now I have an equation, and now I can do things to both sides because I've written this as an equation. All right. So what would I like to do to get this x down from the exponent? Well, I love to lumberjack both sides. Make both sides a log. And we'll make them the log, natural log. So I'll have the natural log of k on the right side, and then we can do the limit first or last. It's our choice. So I'll stick the limit here, and we'll take the limit of the natural log of what we had here, which is 1 plus 1 over x to the x. And we can now use property of logarithms to bring that x down in front of the natural log. And we are on our way to doing what we need to do, which is to create a fraction that is worthy of having L'Hopital's rule applied to it. Okay, so what do we have here? We would have infinity times the natural log of 1, which is 0. And if we go back and look at the list, infinity times 0 is indeterminate. So this is still no good. So I'm going to make this into a fraction like we did on the other page. So we'll rewrite the x as something different, so we can make a fraction out of this. This will still be the natural log of 1 plus 1 over x. The denominator now will be 1 over x. Okay, once again, we're using the principle that x is the same as 1 over x, provided x is not 0. Right, that would be a problem if x was 0. Okay, what's this equal to? It's still equal to the natural log of k. K is some number we don't know. All right, are we in business now? Can we use L'Hopital's rule? Well, let's see. The bottom, the numerator, or the denominator, is going to approach 0, 1 over a big number. And the numerator is the natural log of 1 plus a very small number, basically the natural log of 1. So now you're in the world of 0 over 0. And this can have L'Hopital's rule applied to it. Let me shrink down the text a little bit here so I have some more room. Draw group. There we go. Okay, now let's be careful. We need the derivative of the numerator and the derivative of the denominator. And we still need to take the limit. So let's carry all of our work down. We got the limit as x approaches infinity. Let's start with the denominator. That's very clear. That's negative 1 over x squared. Now the numerator's derivative is going to be 1 over the stuff. So 1 over 1 plus 1 over x times the derivative of 1 plus 1 over x. Well, the derivative of 1 is 0, and the derivative of 1 over x is negative 1 over x squared, which we already have in the denominator. So that's kind of neat, because those are going to cancel out in a second here. This is still equal to the natural log of k. All right, so let's see here. We can remove these common factors, and now on the left side we can finally take our limit. The limit as x goes to infinity of 1 over 1 plus 1 over x. Well, this is going to be 1 over 1 plus pretty close to 0. So we have now 1 is equal to the natural log of k, which tells us that k must be equal to e. And you might recognize that this was one of the ways we defined e, the number e in the very beginning in pre-cal, was this. We didn't say the word limit back then, but we said when x gets very large, this function, this expression, approaches this special number e. And now we have a way to formally prove that to you with L'Hopital's rule. Okay, you're going to use a similar argument by making an equation to do number 55 in section 4.4. That concludes the video. Please email me 2 questions that you had on this lesson, and we will see you in class to practice this some more. Take care.